Sorry, kids.
Hi, it's Mr. Anderson, and today I'm going to be talking about nuclear reactions. Up to this point in physical science, we've mostly been talking about chemistry and chemical reactions. But there's a whole other group of reactions called nuclear reactions. And people, they're no less important, but they maybe are a little less understood. In other words, the nuclear reactions, the fusion reactions found in the sun, are producing the energy that created our food and the light that's coming in this window right here. And so in this podcast, I'm going to try to explain nuclear reactions and where they come from. Now, to understand nuclear reactions, we first have to understand forces in nature. The two major forces that most people are familiar with are going to be gravity
now, Emily, from the last
and then electromagnetism, or the electromagnetic force.
Now,
now, what is gravity? Gravity holds you where you are. And so you stick to the earth because there's a gravitational force that's pulling you down towards it. This was first identified by Newton. The neat thing about it is if we were to shoot you into space and you would be way out here in space, there still is a gravitational force that's holding you towards the planet. Gravity's cool in that it acts over a huge distance, but it's a relatively weak force. In other words, if we zoom down in here where your foot is, so if we look right down here where your foot is, and we try to find your foot looks like this, we'll say. The reason you don't sink through the floor and actually move to the center of the earth is that there is an electromagnetic force here. So there's all these electrons in your foot and all these electrons in the floor, and they're repulsing each other. In other words, my fingers don't move through each other because there's an electromagnetic force pushing them apart. Now, a scientist by the name of Maxwell was able to take the idea of electricity, which was pretty mysterious, combine it with this idea of magnetism, and so we now combine those into one electromagnetic force. And so the two forces that you're familiar with, just walking around forces, are going to be the gravitational force and electromagnetic force. But when we get down to the lower, smaller level, at the level of the nucleus, we find that there are two more forces. Those are called the strong and the weak nuclear forces. So if we look down here in the nucleus, inside the nucleus, let's say these red ones are the protons. The protons have a positive charge, and the neutrons have no charge. They have a neutral charge. And so you would think with the electromagnetic force, all these positive charges in here in the nucleus are actually going to make them push themselves apart. Now, why doesn't that occur? The reason that doesn't occur is that there are all these strong nuclear forces that are holding all these atoms together, or excuse me, the nucleons, the protons and neutrons together. And so the strong nuclear force are all the forces that hold together the nucleus. It wants to fly apart, but these nuclear forces are holding it there. And that's the reason why as atoms get larger and larger and larger and they have more protons in it, we actually have to have more neutrons in the center. There's like a perfect number of neutrons compared to the number of protons you have just to hold the nucleus apart. The problem with the strong nuclear force, and the reason that you don't deal with it, is it only acts over very small distances right here in the middle. The last force is called the weak nuclear force. Weak nuclear force is crazier yet. Sometimes, let me clear this off for a second. Sometimes one of these neutrons will actually turn into a proton. So how do you go from a neutron to a proton? Well, what you give off is an electron which has no mass but has a -1 charge. And so what is accountable for that? It's actually quarks inside this neutron and the protons that are changing, but it's this weak nuclear force that causes that to occur. And then sometimes even something weirder than that happens. Sometimes we'll have one of these protons actually turn into a neutron. And what that does is it gives off a positron. And so when it does that, we have another form of beta decay. But both of those are caused by weak nuclear forces. And so this chart came from our book, but I think it's important to talk about chemical reactions and then nuclear reactions. And so in chemical reactions, what are the players? The players in chemical reactions are the valence electrons. In other words, in all the reactions we've talked about to this point, it's the electrons out here, the electrons at the outside of the atom that actually determines a chemical reaction, what reacts with what. And that's why the periodic table looks the way it does. In a nuclear reaction, however, it's going to be the nucleons that are at play. And so what are the nucleons?
What is this
Nucleons are
thing?
the protons and the neutrons.
No, I don't think so. No, I don't think so. Trust me here.
Okay, what
Rush
starts
me here.
a
Rush me here, please.
chemical reaction?
I don't have me
Well, to start a
alone.
chemical reaction,
What?
you have to have
Over
two
here?
reactants.
Just here happen for
And you have to
relax.
somehow get their valence electrons
That's
close
pretty
enough to
big,
each other
but you
so
do
that you can
that
actually have a chemical
because
reaction. What's
actually
one way we could do
didn't
that?
have
Well, we
me
could
alone.
add pressure to the system. If we
I've got one
squeeze
minute.
these reactants towards each other,
Where?
they're more
What?
likely to react. We could increase the
What?
temperature, and that's going to make them move
What?
around more quickly and more likely
What?
to bounce into each other. Or another way we could do that is we could add a
What's
catalyst
a
to
looking
that. A catalyst
cycler?
is something that's
My
going to
God.
lower
Well,
the
do
activation
you ship?
energy,
Well, do you like coke?
change
Like
in
coke?
energy
No,
through
I
activation.
love
And what that does is it lowers this barrier of energy that must be
Oh,
overcome
it's
in
so
order for a reaction
finished.
to occur.
None.
What about in a
No,
nuclear
it's a looking.
reaction?
No,
In a
it's
nuclear
a looking
reaction, there's two things
cycler.
that could start a nuclear reaction.
No, it's a
Number
looking
one, we could start with
cycler.
particles that are moving faster.
Also,
So if
what?
we bombard
Okay, you're right there,
the nucleon
my
with
friend,
other
all
particles,
over.
protons for example, we can actually start a reaction. Or if we get huge temperature increases, if we increase
Not
the
too bad,
temperature, then we can
here.
have some nuclear
I
reactions
don't
as
have
well.
me alone here.
And that's why we can have the sun, and the
Because
sun
I'm
has enough
here
mass
alone.
to generate that kind of temperature,
I
but we
can't.
don't have fusion
Because I'm not
reactions taking place on our planet.
alone.
What about the end?
What?
What do we create
Have
at
me
the
alone.
end of a chemical
Right
reaction? We create
Dangerous
bonds.
here?
There are
No,
new
it's not
bonds that are
dangerous.
formed.
This is not
Well,
actually
what's
not
formed
a test.
in a nuclear
Everyone can I
reaction?
hear.
In a nuclear
Everyone
reaction,
can
we're going to
happen.
form new,
No,
not
Laura,
bonds,
you
but
don't
since
have
we're
to
changing the amounts of protons, we're going to end up
What?
with
You
new
have a
atoms.
lover. Mover.
The last type is the amount of energy.
Find
The
a
amount of
real
energy in a
potion.
chemical reaction
My
is going to be
city anyway.
really small.
Well, did you see her
Now,
inside?
you wouldn't say that dynamite is a
Smells
small amount of
really.
energy that's released, but it's relatively
What the-
small compared to the amount of energy
What
you get
is this
from a
place?
nuclear
She's
reaction.
here.
Nuclear reaction. we're
Maybe
gonna get
you're an
huge
accident.
amount
No, I don't think so.
of energy.
Here's a right
Why do we
there.
get a huge amount of energy?
First, we have
it actually
3
requires
poles
talking
that
a
are
little bit
winter.
about this
So,
equation.
Lucas,
So you're maybe
you're
familiar
taking
with
up
this.
well.
Equals mc
Check the
squared.
photo. This is
So this is
cold.
Einstein's famous equation. What does
And
it
we call
mean?
it
Well, M
feeling
stands for the
around.
mass. C stands for the speed of
I
light.
figure like you're
And so what do you know
Alice.
about the speed of light? The speed of light is a
I-
huge
Oh, isn't it
number.
right here?
And then we're squaring it, so we're
I
even
know,
making that number
tired.
bigger yet. And so what Einstein said is that you can't create
We
mass, you can't
I remind you.
destroy
It's
mass, but you can convert mass into energy and
There-
energy back into
What?
mass. And so you can take a
Really on
small
it.
amount of mass, like the mass
Or-
inside my finger, and you can create
Yes, I
a
have
huge amount of
plenty here.
energy from that.
There,
And that's
thank you.
all that energy that's
Really
found
has
inside
me
the
return
sun.
here.
We get
Emilybat.
we could take reactions and put them into
Here.
two
No,
different
it's
types.
not,
We have, first
kid.
of all, a fission
You're
reaction.
super
In a
cute.
fission reaction, what you have is a
Huh?
particle that's bombarding
I know, isn't it right? You have
atom,
to
an
spring.
atom that's radioactive.
I
In this
don't
case,
know.
it's uranium
Isn't it a
235.
fake
And
letter?
what that does
A fake
is
letter?
it converts that
I think
into another form of uranium. It
What's
releases
it?
more of these
I don't
particles, and those particles will
Really?
smash
Looks
those,
like-
those parts of atoms are going to smash into other
I
atoms,
think.
which is going to cause this chain
Really?
reaction. So
Well,
this is actually a fission weapon. This is the bomb that was dropped on
what?
I think this is on Nagasaki.
Different growth?
And that's
Yeah,
a
I
fission
know.
reaction.
Isn't
And
it
so
great?
Inside the bomb, you had to have
There
something
was a
that's
result.
able to
Friends brought
create
it
these
just
flying
like with
particles
you.
initially. And then once you
This is
start it,
more like
it's
it.
like a chain reaction.
Let me up,
YouTube
dirty!
has some great videos of a number
Okay,
of
so
different
they-
mouse traps
No,
set up,
did you be here?
with 2 ping pong balls on
What?
each mouse trap.
Here's
And once it gets hit by
you
one
right
ping pong
card.
ball,
But
it's going to cause those
Alice
2 to
has a
fly,
name.
and that hits 4, and that's a fission reaction or a chain
Choice.
reaction.
Sure.
The other major type of a reaction
All
is
about
fusion
your girl.
reactions. And so this
I
is
don't ever ask me. You
a
hate.
fusion
Stop.
reaction that we have
Wait.
is
Hey,
2 different
stop.
particles.
We don't
In this
have
case,
to
these are
alone
protons
here.
that are fusing together.
You don't have me over stop day.
hydrogen.
No,
This
it's
is
not
actually
stop
deuterium.
day. This is beautiful day.
Those neutrons
No
will
way,
fuse
you
together
wrong.
to make
Have
this,
three
which is
twins.
helium-3.
For that case,
So this is
there's
helium,
knowledge.
2
Power.
protons, 1
If this
neutron.
knowledge.
These will then convert
Maybe
into something
forever,
called
if this
beryllium-6,
knowledge.
which is highly
You
unstable.
have knowledge. We're getting here
And
is
so
this
helium
knowledge.
has less mass than the 4
Because you're
original
having what
protons that
knowledge?
were used to create it.
I am
Remember, according to
Master
Einstein's
is
theory,
this
equals
knowledge.
mc squared. The
Choice.
tiny
Pleasure
amount of
is
mass
this
that's
knowledge.
lost when we convert those
Perfect choice.
protons
everyone
into helium, or
knowledge?
the hydrogen into helium,
Of course,
is given
knowledge.
off in the form
We
of
find
energy, and that energy given off the sun comes from
for
fusion.
what?
Now,
I
what would
would
we
never
like to
have me
have on
here.
our planet
You
right now?
told
We only
have
have
me
fission
alone.
reactors, and so we can only
Never
make
do
electricity
that
using
again.
the
You don't
process of
ever
nuclear
have
fission.
knowledge.
The nice thing that we would like to be able to do
Alone.
is just take hydrogen that we
It
have on our
is
planet and fuse that into
Well,
helium.
that
Because there's so much
power
hydrogen
has
here,
me
we could have
here.
almost an
Now,
infinite
isn't it great?
source of
Isn't
energy.
it great?
The problem with that is
You
you
must
have
be
this
alone.
barrier of temperature.
I
You
think
have
you're
enough
alone.
temperature increase so we can actually
Anyways,
fusion take
you
place.
still are everyone here.
Most scientists think this is going to be
Children,
decades away before we
you're
can get there. But the nice thing is once we get
shut.
the fusion
No,
reaction like
don't
that,
shut
we
here.
can fossil fuels
Shit,
like this
this
to
is actual
the chemical
love.
reactions that they have.
No,
And so
wait,
that's
you're
nuclear
right.
reactions. I'll talk a little bit more about radioactivity and
I'm coming.
carbon-14 dating in the next few
Bye-bye.
slides.